In electronics, a flip-flop or latch is a circuit that has two stable states and can be used to store state information. A flip-flop is a bistable multivibrator. The circuit can be made to change state by signals applied to one or more control inputs and will have one or two outputs. It is the basic storage element in sequential logic. Flip-flops and latches are a fundamental building block of digital electronic systems used in computers, communications, and many other types of systems. Flip-flops and latches are used as data storage elements. A flip-flop stores a single bit of data. One of its two states represents a 1, and the other represents a 0. Such data storage can be used for storage of state, and such a circuit is described as sequential logic. When used in a finite state machine, the output and next state depend not only on its current input, but also on its current state. It can also be used for counting of pulses, and for synchronizing variably timed input signals to some reference timing signal. Flip-flops can be either simple or clocked, although the term flip-flop has historically referred generically to both simple and clocked circuits. In modern usage it is common to reserve the term flip-flop exclusively for discussing clocked circuits. The simple ones are commonly called latches. Using this terminology, a latch is level-sensitive, whereas a flip-flop is edge-sensitive. That is, when a latch is enabled it becomes transparent, while a flip-flop's output only changes on a single type of clock edge. History. The first electronic flip-flop was invented in 1918 by the British physicists William Eccles and F.W. Jordan. It was initially called the Eccles-Jordan trigger circuit and consisted of two active elements. The design was used in a 1943 British Colossus code-breaking computer, and such circuits and the transistorized versions were common in computers, even after the introduction of integrated circuits. Though flip-flops made from logic gates are also common now. Early flip-flops were known variously as trigger circuits or multivibrators. According to P. L. Lindley, an engineer at the U.S. Jet Propulsion Laboratory, the flip-flop types detailed below were first discussed in a 1954 UCLA course on computer design by Montgomery Pfister, and then appeared in his book Logical Design of Digital Computers. Lindley was at the time working at Hughes Aircraft under Eldred Nelson, who had coined the term JK for a flip-flop which changed states when both inputs were on. The other names were coined by Pfister. They differ slightly from some of the definitions given below. Lindley explains that he heard the story of the JK flip-flop from Eldred Nelson, who is responsible for coining the term while working at Hughes Aircraft. Flip-flops in use at Hughes at the time were all of the type that came to be known as JK. In designing a logical system, Nelson assigned letters to flip-flop inputs as follows: number 1, A and B, number 2, C and D, number 3, E and F, number 4, G and H, number 5, J and K. Nelson used the notations J input and K input in a patent application filed in 1953. Implementation. Flip-flops can be either simple or clocked. The transparent ones are commonly called latches. The word latch is mainly used for storage elements, while clocked devices are described as flip-flops. Simple flip-flops can be built around a pair of cross-coupled inverting elements. Vacuum tubes, bipolar transistors, field effect transistors, inverters, and inverting logic gates have all been used in practical circuits. Clocked devices are specially designed for synchronous systems. Such devices ignore their inputs except at the transition of a dedicated clock signal. Clocking causes the flip-flop to either change or retain its output signal based upon the values of the input signals at the transition. Some flip-flops change output on the rising edge of the clock, others on the falling edge. Since the elementary amplifying stages are inverting, two stages can be connected in succession to form the needed non-inverting amplifier. In this configuration, each amplifier may be considered as an active inverting feedback network for the other inverting amplifier. Thus, the two stages are connected in a non-inverting loop, although the circuit diagram is usually drawn as a symmetric cross-coupled pair. Flip-flop types. Flip-flops can be divided into common types. The senior, D, T, and JK types are the common ones. The behavior of a particular type can be described by what is termed the characteristic equation, which derives the next output, Q next in terms of the input signal and or the current output. Simple set-reset latches senior nor latch when using static gates as building blocks. The most fundamental latch is the simple senior latch, where S and R stand for set and reset. It can be constructed from a pair of cross-coupled NOR logic gates. The stored bit is present on the output marked Q. While the R and S inputs are both low, feedback maintains the Q and Q outputs in a constant state, with Q the complement of Q. If S is pulsed high while R is held low, then the Q output is forced high, and stays high when S returns to low. Similarly, if R is pulsed high while S is held low, then the Q output is forced low, and stays low when R returns to low. Note: X means don't curve, that is, either 0 or 1 is a valid value. The R equals S equals 1 combination is called a restricted combination or a forbidden state because, as both NOR gates then output zeros, it breaks the logical equation Q equals not Q. The combination is also inappropriate in circuits where both inputs may go low simultaneously. The output would lock at either 1 or 0 depending on the propagation time relations between the gates. To overcome the restricted combination, one can add gates to the inputs that would convert equals to one of the non-restricted combinations. That can be Q equals 1 referred to as an S latch, Q equals 0 referred to as an R latch. This is done in nearly every programmable logic controller. Keep state, referred to as an E latch. Alternatively, the restricted combination can be made to toggle the output. The result is the JK latch. Characteristic: Q plus equals R, Q plus R, S or Q plus equals R, Q plus S. Senior NAND latch. This is an alternate model of the simple senior latch which is built with NAND logic gates. Set and reset now become active low signals, denoted S and R respectively. Otherwise, operation is identical to that of the senior latch. Historically, senior latches have been predominant despite the notational inconvenience of active low inputs. JK latch. The JK latch is much less frequently used than the JK flip-flop. The JK latch follows the following state table. Hence, the JK latch is an senior latch that is made to toggle its output when past the input combination of 11. Unlike the JK flip-flop, the 11-input combination for the JK latch is not very useful because there is no clock that directs toggling. Gated latches and conditional transparency latches are designed to be transparent. That is, input signal changes cause immediate changes in output when several transparent latches follow each other using the same enable signal. Signals can propagate through all of them at once. Alternatively, additional logic can be added to a simple transparent latch to make it non-transparent or opaque when another input is not asserted. By following a transparent high latch with a transparent low latch, a master-slave flip-flop is implemented. Gated senior latch. Asynchronous senior latch can be made by adding a second level of NAND gates to the inverted senior latch. The extra NAND gates further invert the inputs so the simple senior latch becomes a gated senior latch. With E high, the signals can pass through the input gates to the encapsulated latch. All signal combinations except for equals hold then immediately reproduce on the output, i.e., the latch is transparent. With E low, the latch is closed and remains in the state it was left the last time E was high. The enable input is sometimes a clock signal, but more often a read or write strobe. Gated D latch. This latch exploits the fact that, in the two active input combinations of a gated senior latch, R is the complement of S. The input NAND stage converts the 2D input states to these two input combinations for the next senior latch by inverting the data input signal. The low state of the enable signal produces the inactive 11 combination. Thus a gated D latch may be considered as a one-input synchronous senior latch. This configuration prevents application of the restricted input combination. It is also known as transparent latch, data latch, or simply gated latch. It has a data input and an enable signal. The word transparent comes from the fact that, when the enable input is on, the signal propagates directly through the circuit, from the input D to the output Q. Transparent latches are typically used as I/O ports or in asynchronous systems, or in synchronous two-phase systems, where two latches operating on different clock phases prevent data transparency, as in a master-slave flip-flop. Latches are available as integrated circuits, usually with multiple latches per chip. For example, 74HC75 is a quadruple transparent latch in the 7400 series. The truth table shows that when the enable clock input is 0, the D input has no effect on the output. When C is high, the output equals D. Latch. The classic gated latch designs have some undesirable characteristics. They require double rail logic or an inverter. The input-to-output propagation may take up to 3 gate delays. The input-to-output propagation is not constant. Some outputs take 2 gate delays while others take 3. Designers looked for alternatives. A successful alternative is the latch. It requires only a single data input, and its output takes a constant 2 gate delays. In addition, the 2 gate levels of the latch can, in some cases, be merged with the last 2 gate levels of the circuits driving the latch, because many common computational circuits have an OR layer followed by an AND layer as their last 2 levels. Merging the latch function can implement the latch with no additional gate delays. The merge is commonly exploited in the design of pipelined computers, and, in fact, was originally developed by DrJolo to be used in the IBM System 360 Model 91 for that purpose. The latch is hazard-free. If the middle NAND gate is omitted, then one gets the polarity hold latch, which is commonly used because it demands less logic. However, it is susceptible to logic hazard. Intentionally skewing the clock signal can avoid the hazard. D flip-flop. The D flip-flop is widely used. It is also known as a data, or delay, flip-flop. The D flip-flop captures the value of the D input at a definite portion of the clock cycle. That captured value becomes the Q output. At other times, the output Q does not change. The D flip-flop can be viewed as a memory cell, a zero-order hold, or a delay line. Truth table. Most D-type flip-flops in ICs have the capability to be forced to the set or reset state, much like an senior flip-flop. Usually, the illegal S equals R equals 1 condition is resolved in D-type flip-flops. By setting S equals R equals 0, the flip-flop can be used as described above. Here is the truth table for the others S and R possible configurations. These flip-flops are very useful, as they form the basis for shift registers, which are an essential part of many electronic devices. The advantage of the D flip-flop over the D-type transparent latch is that the signal on the D input pin is captured the moment the flip-flop is clocked, and subsequent changes on the D input will be ignored until the next clock event. An exception is that some flip-flops have a reset signal input, which will reset Q, and may be either asynchronous or synchronous with the clock. The above circuit shifts the contents of the register to the right 1-bit position on each active transition of the clock. the input X is shifted into the leftmost bit position. Classical positive edge-triggered D flip-flop. This circuit consists of two stages implemented by senior NAND latches. The input stage processes the clock and data signals to ensure correct input signals for the output stage. If the clock is low, both the output signals of the input stage are high regardless of the data input. The output latch is unaffected and it stores the previous state. When the clock signal changes from low to high, only one of the output voltages goes low and resets the output latch. If D equals 0, the lower output becomes low. If D equals 1, the upper output becomes low. If the clock signal continues staying high, the outputs keep the states regardless of the data input and force the output latch to stay in the corresponding state as the input logical 0 remains active while the clock is high. Hence the role of the output latch is to store the data only while the clock is low. The circuit is closely related to the gated D latch as both the circuits convert the 2D input states to two input combinations for the output senior latch by inverting the data input signal. The difference is that in the gated D latch simple NAND logical gates are used while in the positive edge-triggered D flip-flop senior NAND latches are used for this purpose. The role of these latches is to lock the active output producing low voltage. Thus the positive edge-triggered D flip-flop can also be thought of as a gated D latch with latched input gates. Master-slave edge-triggered D flip-flop. A master-slave D flip-flop is created by connecting two gated D latches in series and inverting the enable input to one of them. It is called master-slave because the second latch in the series only changes in response to a change in the first latch. For a positive edge-triggered master-slave D flip-flop, when the clock signal is low, the enable, seen by the first or master D latch is high. This allows the master latch to store the input value when the clock signal transitions from low to high. As the clock signal goes high, the inverted enable of the first latch goes low and the value seen at the input to the master latch is locked. Nearly simultaneously, the twice-inverted enable of the second or slave D latch transitions from low to high with the clock signal. This allows the signal captured at the rising edge of the clock by the now locked master latch to pass through the slave latch. When the clock signal returns to low, the output of the slave latch is locked, and the value seen at the last rising edge of the clock is held while the master latch begins to accept new values in preparation for the next rising clock edge. By removing the leftmost inverter in the circuit at side A D-type flip-flop, that strobes on the falling edge of a clock signal can be obtained. This has a truth table like this. Edge-triggered dynamic D storage element. An efficient functional alternative to a D flip-flop can be made with dynamic circuits as long as it is clocked often enough. While not a true flip-flop, it is still called a flip-flop for its functional role. While the master-slave D element is triggered on the edge of a clock, its components are each triggered by clock levels. The edge-triggered D flip-flop, as it is called even though it is not a true flip-flop, does not have the master-slave properties. Edge-triggered D flip-flops are often implemented in integrated high-speed operations using dynamic logic. This means that the digital output is stored on parasitic device capacitance while the device is not transitioning. This design of dynamic flip-flops also enables simple resetting since the reset operation can be performed by simply discharging one or more internal nodes. A common dynamic flip-flop variety is the true single-phase clock type, which performs the flip-flop operation with little power and at high speeds. However, dynamic flip-flops will typically not work at static or low clock speeds. Given enough time, leakage paths may discharge the parasitic capacitance enough to cause the flip-flop to enter invalid states. T flip-flop. If the T input is high, the T flip-flop changes state whenever the clock input is strobed. If the T input is low, the flip-flop holds the previous value. This behavior is described by the characteristic equation, and can be described in a truth table. When T is held high, the toggle flip-flop divides the clock frequency by 2, that is, if clock frequency is 4 MHz, the output frequency obtained from the flip-flop will be 2 MHz. This divide by feature has application in various types of digital counters. A T flip-flop can also be built using a JK flip-flop or a D flip-flop. JK flip-flop. The JK flip-flop augments the behavior of the senior flip-flop by interpreting the J equals K equals 1 condition as a flip or toggle command. Specifically, the combination J equals 1, K equals 0 is a command to set the flip-flop. The combination J equals 0, K equals 1 is a command to reset the flip-flop, and the combination J equals K equals 1 is a command to toggle the flip-flop, i.e., change its output to the logical complement of its current value. Setting J equals K equals 0 does not result in a D flip-flop, but rather, will hold the current state. To synthesize a D flip-flop, simply set K equal to the complement of J. Similarly, to synthesize a T flip-flop, set K equal to J. The JK flip-flop is therefore a universal flip-flop, because it can be configured to work as an senior flip-flop, a D flip-flop, or a T flip-flop. The characteristic equation of the JK flip-flop is, and the corresponding truth table is,